Calculating rate of reaction for AQA GCSE Chemistry. So our progression is to go through what is rate of reaction, calculate average rate, graph data, compare the plots for graph data, rate change with time, and then calculating rate at a specific time. In a chemical reaction, reactants are turned into products. So what is rate of reaction? Well, we could say it's how fast a reactant is used up, in which case the rate would be equal to the change in the amount of reactant divided by time taken. Or we could say rate is how fast a chemical is formed, how fast a product is formed, in which case rate would be equal to the change in amount of product over the time taken. The units of rate, of course, will be the change in amount, whether it's be a change in the amount of reactant or the amount of product, divided by a unit of time. It's very important, rate will always have units which include a unit of time. For instance, grams per second or centimeters cubed per minute. And of course, chemically, it may be more correct to turn those into numbers of moles, so moles per second. Calculating average rate. We have a reaction making a gas which then escapes. So our setup would be, for example, a conical flask, a solution and a solid reacting to make bubbles of gas. The gas then escapes through a loosely fitting cotton wool. The balance, electronic balance, will read negative numbers if we start at 0, 0. That indicates a loss of mass, which is equal to the mass of the gas that has escaped. So we achieve data such as this. Every 30 seconds, we take the mass loss and turn that into a mass of gas made in grams. Calculate the average rate of reaction over the first minute. Okay, so that's 0 to 60, and over the second minute, 60 to 120 seconds. Pause, calculate those two average rates of reaction, come back to check and correct when you are ready. Okay, so rate is going to be change in amount of products over the time taken. Okay, the gas is a product, so we're measuring the mass of product made. So change in product over time taken. So in the first minute, we start with 0 grams of gas, and at 1 minute we have 1.5 grams of gas made. So if we then do rate in grams per second, 1.5 divided by 60 is 0.025 grams per second. Notice the unit always has a time unit within it. Try to calculate the rate for the second minute. I'm about to reveal. So here we're going from 1.5 grams to 2.32 grams. So the change is the difference between the two. 2.32 minus 1.5 divided by the time taken, 60 seconds, comes out as 0.014 grams per second. Note, as the reaction proceeds, of course, the rate of reaction slows. So let's discuss the graphing of experimental data. Imagine the experiment previously was repeated, and this time a volume of gas was collected and measured. So every 30 seconds, the volume of gas collected and measured. I've chosen hydrogen as the gas. So the volume is in centimeters cubed, the time is still in seconds. Can you plot a graph of this data? Pause. On graph paper, plot a graph. Come back to check and correct when you are ready. Okay, so the plot looks something like this. The volume of hydrogen gas depended on the time, and therefore the y-axis is the volume of gas and the x-axis is time. You'll see one reading at 60 seconds does not fit the general trend and is referred to as anomalous. And we do not include it in our line of best fit. Now, the line of best fit doesn't have to go through any of the points, but with the plot that I've got, the line of best fit appears to go through most of the points. We leave out the anomalous point from our line of best fit. The graph fills the graph paper as much as possible. I think most exam boards expect you to use at least half the graph paper. So you have to adjust your scale so that at least half the graph paper is used in the data plot. Calculate the average rate of reaction. So there's my plot. Calculate the average rate of reaction. Pause. Come back to check and correct. Okay, so the key point to note is that the reaction ends at 120 seconds. That's the point at which we reach the maximum number of maximum volume of product. So there is no further reaction after 120 seconds. So our average rate is the volume achieved, 70, at the point at which the reaction finished. So 0 to 120 seconds. So we divide 70 by 120 to give us a rate of 0.58 centimeters cubed per second. Just to reiterate, we're dividing by 120, not 180, because the reaction finishes at 120. That is, there is no further production of gas. So if we have two data plots, same experiment, but perhaps at different temperatures or with a varied concentration of one reactant or the other, we want to compare the two and decide which one is faster. Well, our method is to draw a tangent to the curve at time 0, by which we mean we draw a line which touches the curve once, a tangent, and that touching occurs at time 0. So there's my tangent to the curve at time 0 for the orange line. And we can see that if I drew a similar one for the blue line, that the orange line would be steeper, that is, it would have a greater gradient, a greater slope, and therefore it is the faster reaction. So the steeper the curve, the faster the reaction. A bit more scientifically, the steeper the tangent to the curve at time 0, the faster the reaction. In general, as time proceeds, the rate of a reaction slows. The slope of the data plot curve reduces. So here is a plot of data, mass versus time. So we're collecting a product, the mass is increasing with time. I'm going to draw 3 lines. The first one is at close to time 0. We can see the line has a certain steepness, a certain gradient. If I drew another tangent to the curve at 90 seconds, again, this curve is touching this line is touching the curve at one point. It is a tangent. That point is at 90 seconds. We can see that the gradient or the slope of that tangent is less. Therefore, we can conclude that initially the reaction is faster, and then after 90 seconds, it is slower. After around about 190 seconds, or perhaps a bit before, we can see that the gradient of the tangent to the curve actually becomes 0. That is, the reaction has finished. So we can use the idea of the gradient of the tangent to the curve to calculate a rate at a specific time, okay? Not an average, but at a specific time. For instance, the initial rate at time 0. So I can draw a tangent to the curve at time 0. To calculate the gradient, I need to have the rise divided by the run, up divided by along. So to do that, I simply have a look at the rise, which is from 0 to 40, and the run, as it happens, is also 0 to 40. So my initial rate, in other words, at time 0, is 40 divided by 40, which is 1 gram per second. Now, if I want to find the rate at a different time, for instance, 90 seconds, again, I find 90 seconds on the scale. That's what the curve at 90 seconds. I draw a tangent to the curve at 90 seconds, and I work out the rise and the run. So the rise this time is 70 minus 44. 70, but we started at 44. So it's the difference between 70 and 44, which of course is 36. The run, 50 seconds and 125 seconds. So 125 minus 50 is 75. So the difference between these two numbers and the difference between these two numbers is the rise over the run. Now I could have drawn the tangent to the curve any length that I like because it has a constant gradient, but I've just drawn a sufficient length to enable some convenient numbers. So 36 divided by 75 is 0.48 grams per second. So we can see as the reaction proceeds, as we discussed on an earlier slide, the rate of reaction slows. Now, what about the rate at 200 seconds? Well, I hope it's obvious. Rise over run, we have 0 rise. So the rate at 200 seconds is 0. That is, the reaction has ended. So that covers the graphing and interpretation of data plots for rate of reaction data. Repeat the lesson if you think it's necessary. Otherwise, try some textbook questions for which you have the answers, and then move on to some past paper questions. Again, making sure you've got answers available. Thanks for watching. Please like, please subscribe.